All right, here we are in the final section of Chapter 9, the circle chapter. It's the so-called special segment theorems, which is not such a great name. What this is really about is the relationship of segment lengths that are formed in and around circles. So you should think like secants and tangents. Those are the possibilities here. And there'll be relationships between lengths of these. So, the foundation of all of this ultimately is angle-angle similarity, together with new results that were proven in this chapter, notably the inscribed angle theorem. But what does the real work of this? Is the angle-angle similarity theorem that we proved back in the similarity chapter. And what it says is this, and I'm sure you recall, it says roughly that if two triangles have equal angles, then they have proportional sides. And of course, we know that if two angles of one triangle equal two angles of another, the third pair of angles are equal as well. So we get to call it simply angle-angle similarity. So as you see in the diagram, we have two triangles with two angles of one equal to two angles of the other. And then we draw the conclusion that sides which correspond are proportional. And of course, proportionality, as you recall, means that we form ratios of sides that correspond, and then we set those ratios equal to one another. Proportions are equal ratios. Now, as for the work that the inscribed angle theorem will do, well, here's primarily the form of that. Consider the diagram that's in front of you. We have two inscribed angles. They are ABC and ADC. And notice this about them. If you follow out their sides, they both terminate at A and at C, which means that both of those inscribed angles cut the arc AC. But each of them is half the arc that it cuts, which means that they must be equal. Halves of equals are themselves equal. This was one of our corollaries of the inscribed angle theorem, and it's really very powerful. It's what does the sort of chapter 9 part of the work of the results of this chapter. Okay, so here's a possibility that we saw in the previous section, but there we were concerned with angles. Here we're concerned with lengths. So we have a chord and a chord, or if you like, a secant and a secant that intersect inside of a circle. So we have secant AB intersects secant CD. And what we wish to prove is that the product of the pieces of one is equal to the product of the pieces of the other. That is, AE times BE is equal to CE times DE. Now, what you should notice about this conclusion is that it looks very much like what you get if you cross multiply a proportion. And indeed, that's precisely what it is. We could have stated the conclusion as a proportion if we liked. However, that's not usual, that's not typical, so we'll follow tradition and write it as a product equals a product. But the source of that product is a proportion that got cross-multiplied. So the goal then is to derive a proportion. And how will that happen? How does one get at proportions? Get two proportions in this class? Typically, one creates triangles if they're not already present. One proves them similar, usually by angle-angle similarity, and then one writes proportion because sides that correspond will be proportional to one another. And how will that happen? Well, I believe it might happen like this. So what we'll need are a pair of similar triangles. So I'll simply talk you through this. I think you'll be able to understand. So let us construct CB and AD. You could also construct AC and BD. It doesn't make any difference. And then notice that in these two triangles, the CEB and the AED triangle, well, just to note what's obviously true, that we have a pair of equal vertical angles. And then look now at angles C and A. Follow their sides out. They both terminate at B and at D, and moreover, they both cut that arc BD. So by the corollary of the inscribed angle theorem that we noted just a moment ago, those two angles, since they are inscribed and cut the same arc, must be equal to one another, which means now that our two triangles are similar to one another. And I'll write just a small piece of this proof. Be careful about the order. So we now have that CEB is similar to C corresponds to A, and E in one corresponds to E in the other, and D. So that's our similarity statement. And then one ought to be able to write a proportion that involves the four quantities in the conclusion and then cross-multiply and get our conclusion. So that's how this goes. So here's another possibility. We saw this possibility as well when we discussed angles, but here it's side lengths. So here we have two secants that meet outside of the circle. And the conclusion is this, is that the whole of one secant that is AC, times the piece of that secant that lies outside the circle, that is AB, is equal to the whole of the second secant times the piece of the second secant that lies outside the circle, that is AE times AD. Now, as for how one would prove this, well, the technique is the same as before. The technique is to create triangles, prove them similar to one another, and then once one has that, one writes a proportion and then cross multiplies it. Now, as for the triangles that will be similar to one another, I believe they're CAD and EBA. Okay? Now, notice that those two triangles have angle A in common, and notice as well that angle C in one and angle E in the other, they both cut arc BD, which means that they are equal to one another. So now we do have that two angles of CAD are equal to two angles of EBA, which means they're similar, which means we can write a proportion. Write a proportion that involves the four quantities in the conclusion, cross multiply, and you should have your conclusion. So here's another possibility. We have a secant and a tangent that meet outside the circle. One needs to create two triangles. And like in the case that we just saw, the triangles one creates will like overlap. Indeed, I think one will be part of the other. One proves they're similar and so on. Notice something about this. This should remind you a little bit of the work that we did in the similarity chapter, actually quite a bit. Indeed, that feature that we found that in some cases, do you remember the case where we had the right triangle and dropped the altitude to the hypotenuse and found ourselves with three similar triangles? We could write proportions in which a quantity occurred more than once because it represents a side length that was a side of more than one triangle, which means that in a proportion, that quantity could appear twice, which means that potentially when we cross multiply, that quantity gets multiplied by itself. Well, look at that, okay? In this case, what we're supposed to prove, should have written prove, what we're supposed to prove is that AB squared is AD times AC. That is the tangent squared is the whole of the secant times the piece outside. AB squared. Okay, now what that will mean is this, is that in the proportion that you will write, a proportion that will follow from the similarity of two triangles, AB will occur twice. And when you cross multiply, AB will be multiplied by itself. Now, as you recall, this feature of similarity, this possibility of similarity, we call that self-similarity, gives rise to, ultimately a proof of the Pythagorean theorem, right? And this possibility that we could have a quantity squared, get that out of similarity, well, that's ultimately what leads us to, the famous a squared plus b squared is equal to c squared. And as a matter of fact, I don't talk about this here with you, but on the worksheet you will find that I guide you through or sort of bring you to the edge of another proof of the Pythagorean theorem by the introduction of a circle into a right triangle. You'll see that, and then it'll be our second proof of the Pythagorean theorem.